In the vast expanse of space, gravity reigns supreme. It is the invisible hand that orchestrates the grand cosmic symphony, dictating the movements of celestial bodies across the universe. It dictates the motion of planets, stars, and galaxies, ensuring that they follow precise paths through the cosmos. This gravitational force is what keeps our solar system in harmony, with planets orbiting the sun in a delicate balance. Yet, within this cosmic dance, there exist pockets of stability, points where the gravitational forces of celestial bodies find a delicate balance. These points are like cosmic oases, where the gravitational pull of two large bodies, such as the Earth and the Sun, create regions of equilibrium. These are the Lagrange points, named after the Italian-French mathematician Joseph Louis Lagrange, who first described them in 1772. Lagrange's work laid the foundation for our understanding of these unique points in space, where the gravitational forces and the orbital motion of objects create a stable environment. Imagine a celestial ballet with two massive partners, like the Sun and Earth. In this dance, the Lagrange points are like specific spots on the dance floor, where a third, much smaller dancer could join in and maintain a stable position relative to the two larger dancers. This smaller dancer could be a satellite or a spacecraft, finding a perfect spot to stay in sync with the larger bodies. Lagrange points are like specific spots on the dance floor where a third, much smaller dancer could join in and maintain a stable position relative to the two larger dancers. These points are not just theoretical. They have practical applications in space exploration and astronomy. These points, 5 in total for each two-body system, are where the gravitational pull of the two large bodies and the centrifugal force experienced by the smaller object all cancel each other out. This delicate balance creates regions where objects can remain relatively stationary with minimal fuel consumption, making them ideal for long-term missions. Lagrange points are not like fixed points in space. They move as the larger bodies orbit each other, creating a dynamic environment. This means that the position of a Lagrange point is constantly changing, but the balance of forces remains consistent. They move as the larger bodies orbit each other. This dynamic nature of Lagrange points means that they can be used for a variety of purposes, from positioning satellites to serving as observation points for telescopes. Understanding these celestial sweet spots is crucial for space exploration, as they offer unique advantages for positioning spacecraft and telescopes. For instance, the James Webb Space Telescope is positioned at the second Lagrange point, or L2, where it can observe the universe without the interference of Earth's shadow. Similarly, other missions take advantage of these points to reduce fuel consumption and maintain stable orbits. By utilizing Lagrange points, space agencies can optimize their missions, ensuring that spacecraft remain in stable positions with minimal adjustments. This not only extends the lifespan of missions, but also allows for continuous observation and data collection. The contributions of Joseph Louis Lagrange have had a lasting impact on our understanding of celestial mechanics. His work continues to influence modern space exploration, providing a framework for navigating the complexities of gravitational forces. As we look to the future, Lagrange points will play an increasingly important role in our quest to explore the cosmos. Future missions are already being planned to take advantage of these unique regions, paving the way for new discoveries and advancements in space science. In the vastness of space, Lagrange points stand out as beacons of stability, offering a glimpse into the intricate dance of gravitational forces. They remind us of the delicate balance that governs our universe and the endless possibilities that lie ahead in our exploration of the cosmos. To understand Lagrange points, we need to grasp the interplay of forces at play. Imagine a spacecraft orbiting the Sun. The Sun's gravity pulls it inwards, while the spacecraft's forward motion creates an outward centrifugal force. In a stable orbit, these forces are balanced. Lagrange points introduce a third player, another celestial body like Earth in our Sun spacecraft example. Now, the spacecraft experiences gravitational forces from both the Sun and Earth, in addition to its own centrifugal force. At specific points in space, these forces interact to create a stable equilibrium. These points of equilibrium are the Lagrange points. They are not static. They move as the Earth orbits the Sun, always maintaining their relative positions. The first Lagrange point, commonly referred to as L1, is a fascinating location in space. It lies directly between the Sun and Earth, at a distance of approximately 1.5 million kilometers from our planet. This point is one of the 5 Lagrange points in the Earth-Sun system, where the gravitational forces of the two large bodies, the Sun and Earth, and the centrifugal force of an object in orbit, combine to create a stable location. At L1, the gravitational pull of the Sun and Earth combine in such a way that an object with a much smaller mass, like a satellite, can maintain a stable position relative to the Earth and Sun. This means that a satellite placed at L1 will orbit the Sun at the same rate as the Earth, effectively staying in a fixed position relative to our planet. This unique balance of forces makes L1 an ideal spot for certain types of space missions. This unique location makes L1 particularly ideal for solar observation. Because it is situated between the Earth and the Sun, a satellite at L1 has an uninterrupted view of the Sun. This allows for continuous monitoring of solar activity, which is crucial for understanding the Sun's behavior and its impact on the solar system. Satellites placed at L1 not only have a clear view of the Sun, but also experience a constant stream of solar wind particles. These particles are emitted by the Sun and can have significant effects on space weather, which in turn can impact satellite operations, communications, and even power grids on Earth. By studying these particles, scientists can better predict and mitigate the effects of solar storms. One notable inhabitant of the L1 point is the Solar and Heliospheric Observatory, or SOHO. This spacecraft is a joint mission between NASA and the European Space Agency, and it has been stationed at L1 since its launch in 1995. SOHO's primary mission is to study the Sun, from its deep core to the outer corona, and to provide early warning of solar storms. Over the years, SOHO has provided invaluable data about the Sun. It has captured stunning images of the Sun's corona, the outermost layer of the Sun's atmosphere, and has observed numerous solar flares and coronal mass ejections. These observations have greatly enhanced our understanding of solar dynamics and have helped to improve space weather forecasting, which is essential for protecting both space-based and ground-based technological systems. Section 4L2, the Sun-Earth Outer Point, home of the James Webb Space Telescope. Located about 1.5 million kilometers on the opposite side of Earth from the Sun, L2 offers a different set of advantages for space exploration. This unique position allows spacecraft to maintain a stable orbit with minimal fuel consumption, making it an ideal spot for long-term missions. At this point, the combined gravity of the Sun and Earth allows a spacecraft to orbit at the same rate as Earth while remaining in Earth's shadow. This means that the spacecraft can stay in a relatively fixed position relative to Earth and the Sun, providing a consistent environment for scientific observations. This provides a stable environment with minimal interference from sunlight and Earth's radiation. The lack of direct sunlight and the reduced influence of Earth's thermal radiation create an exceptionally cold and stable environment, which is crucial for the sensitive instruments aboard space telescopes. This makes L2 an ideal location for space telescopes that require extremely sensitive instruments. The stability and cold temperatures at L2 allow these instruments to operate at their best, capturing faint signals from distant objects in the universe. The James Webb Space Telescope, launched in 2021, is currently stationed at L2. This position allows it to take advantage of the unique conditions at L2 to conduct groundbreaking scientific research. JWST's infrared instruments benefit from the cold, stable environment, allowing it to peer deep into the universe and observe the faintest objects. By operating in the infrared spectrum, JWST can see through cosmic dust clouds and reveal hidden structures in the universe, providing new insights into the formation of stars and galaxies. The data collected by JWST is transmitted back to Earth, where scientists analyze it to uncover the mysteries of the cosmos. This information helps us understand the origins of the universe, the formation of planetary systems, and the potential for life on other planets. The James Webb Space Telescope represents a significant leap forward in our ability to explore the universe. Its advanced technology and strategic location at L2 enable it to perform tasks that were previously impossible, pushing the boundaries of our knowledge and opening new frontiers in space exploration. As we look to the future, the success of JWST at L2 paves the way for future missions to utilize this advantageous position. The lessons learned from JWST will inform the design and deployment of next-generation space telescopes and other scientific instruments, ensuring that L2 remains a vital hub for space exploration for years to come. Section 5, L3, Hiding Behind the Sun. L3 is a point of theoretical interest rather than practical use. Located on the opposite side of the Sun from Earth, L3 is permanently hidden from our view. This hidden nature has fueled science fiction stories about a counter-Earth lurking at L3. However, in reality, the gravitational influence of other planets in our solar system would make it impossible for a large object to remain stable at L3. Any object at L3 would be perturbed and eventually drift away. Section 6L4 and L5, Sharing Orbits with Stability. The last two Lagrange points, L4 and L5, are unique. These points lie along Earth's orbit around the Sun, with L4 ahead of Earth and L5 trailing behind. These points are stable due to a delicate balance of gravitational forces and the Coriolis effect, which arises from the rotating reference frame of the Earth-Sun system. Objects at L4 and L5 are effectively trapped in these stable regions, often referred to as Trojan points. In our solar system, Jupiter's L4 and L5 points are home to thousands of asteroids known as Trojan asteroids. These asteroids share Jupiter's orbit, with one group always ahead of Jupiter and the other always trailing behind.